Hi, I'm Simon. I work at the Actimize division of NICE. We're all about the prevention of financial crime. Our main product is in anti-money laundering, our biggest product. Some of our unique challenges are extremely imbalanced data sets. Real sort of needle in a haystack cases. The actual underlying crime level is just fractions of a percent. We're looking at criminals who are changing their tactics rapidly on the one hand, and on the other hand, we're looking at a regulated environment. We're looking at banks who are kind of in a conservative business environment. If that's of interest to anybody, then drop me an email. We're talking today about automated ML. In general, those are systems that take out some of the boring grunt work that a data scientist might be doing. It's becoming more and more into the mainstream. There was a year and a half ago, there was an article in the New York Times. I don't think it gets much more mainstream than that. I'm actually going to start from the for some conclusions. The reason is that people, when they hear about this, start to get worried about job security. So the question about will I become unemployed, the answer is no, but so first of all, my overall outlook here is to look at these systems more as a sort of productivity tool. I'll give a quick parallel. My grandfather was an accountant in a factory in the north of England. Once every quarter, they would want to get a snapshot of what's going in the company. They'd put all the figures into a big piece of paper called a spreadsheet, and they would add up all the columns, they would add up all the rows, and in the end, they'd get a picture of what's going on in the company. If you made a mistake, if you wanted to see what would happen if you added 20 employees, then come back in 2 weeks, we'll give you an answer. Of course, in 1979, VisiCalc came out, and everybody knows what happened next. But the question is, after 1979, were there more accountants or less accountants? And the answer is there are actually more accountants. But what were the accountants doing? They became business advisors. They're looking at models. They're looking at tax strategy. They're looking at things like projections and what-if scenarios. But what did happen is there was a job called a bookkeeper. Those are pretty much extinct. I don't think I know any bookkeepers today. So what are some of the things that we're looking at automating? This list comes directly from Wikipedia. I've highlighted some of what I think are the more realistic things in yellow here. So we've got automated type detection. That's something you can do pretty much in R today, feature selection, automated model selection. Hyperparameter optimization is interesting because a few years ago, maybe people would have taken default values for parameters of models that have done some hand tuning not that many years ago, but now pretty much everybody will at least make use of hyperparameter optimization to find some of the parameters. So that's an example of some sort of automated ML that we're using now without even really thinking about it. Other things are pipeline selection under time and different constraints, and visualizations of results, visualizations of models, visualizations of data that you can do all that sort of thing on an automated basis. Some of the notable systems that are out there today, I'll start with Google AutoML because they have actually hijacked the term AutoML. But what they do is for neural networks. They're optimizing architecture, just searching for optimal architectures in deep learning. There's an open source parallel to that called AutoKeras, I think. H2O driverless, popular data robot are probably the market leaders. A couple of Israeli companies. There's Firefly. There's some nice guys who the idea is you upload some data to their cloud. You can configure a few things, and at the end, you'll get a good model out of it. Spark Beyond, more or less, they're looking at feature enrichments. You give them your features, they'll try and connect it to outside data sources, additional data sources. They'll try and understand what your features are. Most of the commercial systems will have fairly slick UIs. They'll be somewhat accessible to non-expert users, to business users. On the other hand, you've got the open source systems, maybe less accessible, but maybe more flexible. AutoScaler and Teapot are Python systems. They both come out of academia. They're both fairly similar. They'll build you some features and find you like a model ensemble out of your data. AutoScaler works on Bayesian optimization. Teapot does genetic algorithms for optimization, or evolutionary algorithms, I think we're supposed to call them nowadays. I'll talk a little bit later on about AutoScaler. That's the system that I decided to use. The reason was basically just got it working more quickly, completely arbitrary. Actually, if you look on GitHub, you'll see, according to most metrics, that the Teapot is the more popular project. H2O Flow is a cut-down version of the H2O driverless with the sort of UI. Feature Tools is interesting. They talk there about deep feature synthesis. What that is taking relational data, doing lots and lots of aggregations until you find something that's kind of predictive in a more or less brute force manner. So what we decided to do was to take some of these open source tools and to try and see if we could get in somewhere in the same ballpark as the commercial systems that are out there today. So it's probably not much of a surprise here to people that in order to get a good model, you basically need first of all good features. That's the first thing you need to do. So we wanted to build a generic pipeline that would take any sort of data and build some features from some sort of generic features from that data. So when we're talking about pipelines, most of us work with pipelines, maybe not in a formal manner, but we're talking about taking raw data on one side, applying a sequence of operations on that data, and at the end you have some sort of estimator that you can do predictions with. But there is actually a more formal, you could call it, interfaces that some of these frameworks have. The first one to come out with it was Python scikit-learn. Spark took inspiration from that. They said as much in the documentation. It's basically a copy of it. There's also an R version that I've never tried. So what it is that you have pipelines are made up of these steps or elements that are called transformers. And each transformer will transform the data, will do an operation on the data, from the pre-processing all the way to feature creation. And the actual estimators at the end are also a type of transformer. There's just a transformer with the predictor and some metrics attached to it. So each transformer will minimally have a fit method that does the actual learning. It will then store that state. And then once you've got that state learned, then you can transform any subsequent data that comes through your pipeline. And you can make your own transformers. All you have to do is implement the fit and the transform method minimally. You actually get some very good cheap wins for that. Doing something like cross-validation, it gives you data hygiene. It will stop data leaking from the validation fold into the training fold, and you basically get that for free once you're using a pipeline. And also in hyperparameter optimization, you can now optimize your features as well as the model all in one go. You can do that in one shot, basically. And the other good win there is you've got a credible path to deployment. You can take the pipeline, put it straight into production, theoretically. So we decided to use scikit-learn pipelines. There is one quality of life issue there, that they will accept pandas data sets. So pandas data set will have row headers, column headers, metadata. You put it through some of the out-of-the-box scikit-learn transformers, and you'll get a NumPy array out of it with no metadata. You'll just get raw data out of it, and you'll lose it all. And our solution was just to wrap the out-of-the-box transformers in a thin layer that would reapply the metadata basically after you've done the transformation. So here's a very quick code example at this time of the evening. So we wanted to create a transformer that would take any column that just only had a single value in it and get rid of it, because it's no use to us in a machine learning model. You can see here there's a fit model. It takes in a data frame called X, and here we're just selecting all the column names that have one value in them, and we're putting it into this drop columns variable, and that's storing our state of what columns it is we want to drop. And then we have a transformer, again taking a data frame, or it could just be a row of data, and it will do the actual dropping of those columns. And you can then, with those 6 lines of code, you can apply that pretty much any way you want to. You can get rid of that sort of data from your data set. So we wanted to do those sort of generic operations on data. So lots of data cleansing. Some of our data, quite a lot of our data is kind of highly correlated, lots of nulls, doing all that sort of cleanup, the things that you can do on a more or less automated basis so that without thinking about it. Then identifying categorical data, numeric data, date data, and handling that in its own specific way. For example, with date handling, you identify any date columns you have, and you then parse them into its elements, hour of the day, day of the week, that sort of thing, create those sort of features, and then do some arithmetic on the dates. The difference between all the different dates can be very useful in sort of crime, when the last event happened, all of that sort of thing. And the next stage is just to do some feature selection, whatever your preferred method is. So once we had these features, we dropped it into AutoSKLearn, just completely with the defaults. You can configure it quite extensively, but didn't bother. Because there was rather a lot of data, we put it onto a big cloud instance with multiple CPUs, ran it in parallel, let it run for like 12 hours, and in the end we got back an ensemble, a model ensemble. Not very surprising, probably. Lots of basically different versions of gradient boosted trees. Wasn't really very surprising, but all optimized slightly differently. In general, the results were comparable to a hand-rolled, to a handmade model, and also in the same ballpark as the leading commercial solutions out there that we tried. So if we can do all of that, then the question is, why would you need a data scientist? So one of the pitfalls we found is that we tried it on some online banking fraud data, and the number one feature that came from numerical IP addresses. So instead of having dotted quad IP addresses, we store it as a number. The system picked that up as an important variable. And but anybody who knows how residential ISPs work, you have dynamic IP that will change every few weeks in a typical home. And so a data scientist, anyone with common sense, can see that after a few weeks your model's going to degrade quite significantly. So that's the sort of thing that a data scientist would be able to spot that an automated system wouldn't be able to. in general, the sort of things we're looking at are that the data scientist brings to the table. Obviously, the domain knowledge. In our field, there's lots of things that you can't include in models because they're considered discriminatory. You're not allowed to, in certain applications, do things based on age or race or other things. And sometimes as well, some of these fields are proxy fields. If you're not allowed to discriminate against a certain demographic, but if you're looking at zip codes, maybe some zip code is made up of predominantly of one demographic, then maybe you shouldn't be using the zip code either. So that's a lot of domain knowledge that's needed. Obviously, you're asking the right sort of questions. Very important is what metrics you're using, and very, very important is what loss functions you're looking at. I haven't seen any of these systems that really can search through different loss functions in any sensible way. That's something that the data scientist definitely needs to keep an eye on. And obviously, that you're looking at the right data. Some of the takeaways from our research here is that AutoML is here. You can look at these, specifically these open source systems. I would urge anybody to do so. The research that you see here was really a matter of a few days only. We managed to get it all up and running exactly how we wanted to. So again, look at it as a productivity tool. I think in a lot of places that you wouldn't have in the past been able to do models because it would just been too expensive. Lots and lots of applications where data science is just not feasible today just because of the cost. I think it will bring it into the range of into feasibility, more common usage. My personal opinion is that I wouldn't put any of these systems into production without somebody analyzing it, looking at it, seeing exactly what's in there, what features it's taking, really giving it the full analysis. And that pretty much is that's pretty much the state of the art today. If there's any questions, I'm happy to hear them. Yeah.
Do you have this research summarized somewhere?
Here. Is it here?
Quick question.
Yeah.
A bit related. Are you working with Scala or PySpark?
This was all. Yeah. So that was like I said, the scikit-learn. That was Python. Yeah. In Python, the custom transformers. It wasn't with PySpark, it's with scikit-learn. Yeah, but it's available on Spark. I did it maybe a year and a half ago on Spark, so it's been available since at least 2.0. You can do it. Yeah. So there's custom transformers. Yeah. Yeah, so it's, the fraud solution is real time when the transaction comes in or even a login. We're looking at that. So all our models have to work in basically near real time, a very tight time budget.
And when you have the details of someone come in, do you check that those details against public databases?
A limited amount. For example, IP address. You can enrich that. You can get coordinates. So you can get lots of information out of IP addresses, things like that. But only things that we can do more or less in real time. Yeah. Hi.
How about feature selection?
Yeah.
You use the methods that are available in scikit-learn in order to choose.
Yeah. So in this case, we did actually built a random forest model and then saw what the most important features were there, what gave the most gain, and took the top end features or whatever into the model.
Because there are some issues with using actually the random forest
Mhm.
feature selection. Sometimes there's some kind of
Yeah, yeah.
non-optimal performance for certain use cases.
Yeah, so I mean, I said feature selection very generically because once you've got, once you're using the transformer sort of interface, you can swap in lots of different feature selection methods, and the more or less you can try out lots of different ones. So it's very flexible like that. If you find something's not fit for purpose, then you can just try a different method. And I tried K-best, I tried random forest, lots of different. Okay, thank you. Have a safe journey home.